Welcome back. We will continue our discussion on determination of polymer molecular weight, and in this lecture I will talk about dilute solution viscometry, which is utilized to determine viscosity average molecular weight, and I will talk about static light scattering. Now, when you talk about viscometry, we are dealing with viscosity of a solution, and these are the definitions of different types of viscosity we should remember, and there are some common terminology which are very frequently used even now and corresponding IUPAC recommendation. For example, eta R is a ratio of eta and eta naught, where eta is the viscosity of the solvent and eta is the viscosity of polymer solution of concentration C. Again, C is mass per unit volume. Now, this is a ratio, eta R is a ratio, so it is unitless, it should not be a viscosity, it is a ratio of two viscosities. Hence, instead of naming it as relative viscosity, IUPAC suggested to be more technically correct as viscosity ratio. Similarly, these other expressions are named by IUPAC, these are the terminologies, but even now most of the literature are basically reports this terminology when talk about this expression. Intrinsic viscosity is very important. It deals with the intrinsic ability of a polymer to increase the viscosity of a particular solvent at a given temperature. We have seen this expression earlier. A and K are the two constant terms which are constant for a particular polymer temperature solvent combination. If we change one of these three, then K and A value changes, and this is intrinsic viscosity, and this is defined as specific viscosity divided by C at C tends to 0. For a dilute solution, we can assume that the specific viscosity of the solution can be obtained by adding up the specific viscosity of the individual polymer molecule in a polydispersed polymer sample. We also can then, for a dilute solution, we can write this expression that for individual polymer chain I, the specific viscosity can be written as the intrinsic viscosity for the particular chain multiplied by concentration using this expression. And we can also write that intrinsic viscosity of a particular chain is given by this expression, where we are basically using the molecular weight of that particular chain. Hence, we can write intrinsic viscosity as summation of the intrinsic viscosity of individual molecule and total concentration as summation of the concentration of individual molecules. We can replace this with this term, and this we can replace with this term, and this term Ci by summation of Ci is the weight fraction for individual chains. Hence, this is a constant, we can take this out of the summation. Hence, we can write, if we compare this expression with this expression, we can say that mv is given by this expression. Similarly, we can also write this way, concentration we can write in terms of number of moles of that particular chain, V is the volume, this is the molecular weight of individual chains, and we can write this expression, and this comparing this expression with this expression, we can write mv in this way also. These are two same expression, they basically we are expressing in terms of weight fraction, because this is the easier way, because we generally deals with polymer weight samples rather than number of moles when we make a solution. And for a Gaussian chain like random coils, this value of A is between 0.5 and 0.8, hence the value of mv, viscosity average molecular weight, lies between mn and mw, but closer to mw. And if you have a very elongated cylindrical type polymer chain, then A value even goes beyond 0.8, is closer to 1. In that case, the mv value would be very close to weight average molecular weight. But for normal random coil Gaussian chain, the mv value is between mn and mw, but closer to mw. Now, this expression we have used earlier. I have written this Mark-Hoyne equation earlier, but sometimes it is also called Mark-Hoyne-Sakurada equation. K value are constant for a given polymer solvent temperature Kelvin, and normally those values are linear chain. For theta condition, A is 0.5 and K increases with increasing the value of A for flexible chain, and the typical value are given, and this is very difficult for copolymer to calculate. Now, this is the Mark-Hoyne equation. We have talked about this again, and to find out the viscosity average molecular weight, we can plot log, we have intrinsic viscosity is given by K mv A. So, if we take logarithm of both sides, we get log K plus A log mv. So, if we plot this in the y axis and this in the x axis, from the slope we can get the value of A, and from the intercept we can get the value of log K. Now, this value intrinsic viscosity, we discussed earlier that it depends on the density of a polymer coil. If there are, for a given molecular weight, if we have more branches, then the coil density goes off, hydrodynamic volume comes down, intrinsic viscosity also comes down. So, depending on the polymer architecture, this intrinsic viscosity can be changed, hence this K and A value also change. So, basically for lightly branched polymers we get lower intrinsic viscosity value. So, this plot have a lower slope, A value is lower. Similarly, very highly branched A value is even lower. And if we have a very elongated polymer, then we can have a even steeper slope, because that A value will go up. Now, the question comes, if you basically has synthesized a new polymer molecule, then how can we get the molecular weight? What is the way we can get the molecular weight for unknown polymer molecule? If we can basically take, we can make several concentration of polymer solution and find out eta for those solution, and then if we know the value for K and A for that particular polymer solvent temperature combination, then from the intrinsic viscosity we can find out the value of mv. But if we do not know the value of K and A, then how can we find out? So, in that case we need a calibration using, so we need to find out log eta and log mv, and we need to find out calibration from which we can get log k and a value. So, for that, for generating this straight line, we need to have same polymer with different molecular weight, then only we can find out this log mv. Now, how to, if we do not know the molecular weight itself, how can we plot this? That is a very difficult thing to do, or it is not possible. So, for that what we need to do, we need to get same polymer sample with different molecular weight, narrow disperse, and measure the molecular weight of those different polymer sample using some other absolute techniques like say light scattering, which I will discuss little later, or say osmometry, where we can get absolute Mn value. And because we will consider having very narrow dispersed polymer sample, we can consider that those Mn value or Mw value which we measured using that absolute technique as equal to Mv. Hence, we can use those values and generate a calibration curve from which we can get the value of K and A. Hence, this technique of determining molecular weight depends on a calibration curve which need to be constructed by determining the molecular weight of a set of polymer sample using other techniques, which means this is a relative technique, not a absolute technique, because it depends on a calibration curve which need to be constructed using a set of polymer of known molecular weight which need to be determined by some other techniques. Hence, it is a relative technique. Now, how to get the value of intrinsic viscosity? Now, this variation of solution viscosity with increasing concentration can be expressed as a power series, and these are there are two expression can be possible. So, this is Huggins equation, and this is valid for dilute solution, and for dilute solution we can basically plot eta Sp by C with concentration and get this. So, from this intercept we can get the value of eta. Or there is another expression, Kramer equation, which plots this term with concentration. So, for that we can plot ln eta r by C with concentration, and we will get ideally same intercept. So, using either of this expression or using both expression to be sure, we can get the value of intrinsic viscosity. So, for that we need to calculate either eta Sp or this for a number of solutions having different concentration, and eta Sp is nothing but viscosity unit. For that you need to find out the viscosity of the solvent as well as viscosity of the different solutions. You can use any standard technique. In our standard teaching labs, we have this Oswald viscometer or Woodman viscometer, which can be used to measure the viscosity of polymer solution, or there are nowadays very sophisticated techniques which can give directly the viscosity of the solution very quickly. So, we can use one of those viscometers to find out the viscosity value for different solutions having different concentration of polymer and the solvent, and for which we can calculate this eta S p by C and plot as a function of concentration of solution, and from which we can get the intrinsic viscosity value. And if we know the intrinsic viscosity value with knowledge from K and A, we can find out the molecular weight, which so eta K and A will give us the value of AMV. Now, for lot of polymers solvent temperature combination, these values are available in the literature. So, we can take advantage of this value available in the literature, and we can measure the intrinsic viscosity to find out AMV. So, most of the common polymers we can use these techniques to find out the AMV for the newly synthesized polymer also. Now, we can use viscometry or viscosity measurements to find out the molecular dimension. The size of the polymer chain in any solvent can be obtained directly from light scattering measurement, but if the polymer coil is large enough to scatter in an asymmetric manner. We will discuss that. If the size of the polymer chain is large enough that it scatter light in a asymmetric manner, then we can use light scattering technique to find out directly the size of the molecule. But if the chain is not long enough, then light scattering technique is not sufficient, then we can use viscometry to find out the size indirectly. An average dimension of polymer molecule in solution can be derived simply from their intrinsic viscosity and molecular weight. We have seen this expression that hydrodynamic volume at very dilute solution is given by this expression, where m is the molecular weight, this intrinsic viscosity, and this is Avogadro number. And the unperturbed dimension of the polymer chain can be estimated from the knowledge of intrinsic viscosity in theta solvent. I will come to that. So, we have seen the Flory-Fox equation, where intrinsic viscosity is given by this expression, where k theta is given by this, and we can also express, this is the expansion factor, we can express the same intrinsic viscosity by another expression related similar. In this case we are talking about radius of gyration, in this case we are talking about end to end RMS end to end distance. Now, these two constant are normally independent of the solvent and the molecular weight of the polymer, though it often depends on some extent on temperature. So, these expression we have seen earlier, this is the same expression, one is expressed in terms of radius of gyration and the other is expressed as in terms of average end to end distance. So, from this expression we know, or we can basically estimate that intrinsic viscosity would depends on the stiffness of the polymer chain. This ratio gives us the stiffness of polymer chain. So, intrinsic viscosity relates to the stiffness of the polymer chain, also on the molecular weight of the polymer and the polymer solvent temperature combination, which gives this value of this expansion factor. For theta solvent, the value of expansion factor is 1, as we have earlier discussed. Hence, this expansion factor can be obtained by measuring the intrinsic viscosity for any particular solvent and intrinsic viscosity in theta solvent. Remember, I have just given an example that this acetonitrile is a theta solvent for PMMA at 30 degrees centigrade. So, osmotic pressure pi by C did not change with concentration. So, we can use the intrinsic viscosity in theta solvent and in another solvent to get the value of this expansion factor in terms of radius of gyration or end to end distance. So, if you know the intrinsic viscosity at theta solvent, then this expression can be written like this, where phi is the Flory constant and this should have a universal value of all for all linear polymers in all solvents. So, we can find out the intrinsic viscosity in theta solvent, and if we know the molecular weight for that particular sample, then we can determine or we can get the value of the chain dimension, the average end to end distance or average radius of gyration for the chains which are even not long enough to get or determined by light scattering technique. So, this is the indirect way by measuring the intrinsic viscosity of a polymer sample in theta solvent, and also from the knowledge of molecular weight of that particular sample, we can use this expression to find out or to guess or to estimate the size in terms of RMS end to end distance or radius of gyration by this expression. Next, I will move to light scattering technique for determining molecular weight. Before that, I just want to talk little bit about light scattering phenomena. We have seen light scattering phenomena in nature, and the reason for the blue sky or white clouds are basically due to light scattering of the gaseous molecules present in atmosphere. Similarly, red sunset or a beam of light coming through window in a dark room, they are all due to the light scattered by the atmosphere particle. Similarly, poor visibility of fog is due to this light scattering of the water droplets, small water droplets present in air, and we have seen several laser shows using laser beams. We can basically visualize the beam because of the scattering caused by the particles in the atmosphere. How does light scatter? When a light which is electromagnetic radiation interacts with a matter, it causes the charges in a molecule or a matter to polarize. Basically, it actually induces some dipole. Now, that dipole oscillates in sync with the electric field of the incident light, and we know that oscillating charges actually radiate light, and those are the scattered light, and light gets scattered in all direction from the sample. And how much light will scatter or what is the intensity of scattered light will depend upon the extent of polarization induced by the light, incident light, and that depends on the polarizability of the matter. Hence, light, the amount of light scattered or intensity of light, scattered light will depend on the value of polarizability of the matter. Now, this is a simplified diagram how a light scattering measurement is done, where an incident beam is applied to a sample and light scattered in all directions. We can place these detectors in different angle to find out the amount of light scattered in that particular angle. So, this is the scattering angle theta, and this is the transmitted beam, which is theta is equal to 0, and this distance is between the detector and the sample we are mentioning at r. Now, as the light gets scattered, we can have two types of measurement. So, with time, if we plot the intensity of light with time, then we can see that there are fluctuating intensity with time, and if in this case the time scale in microseconds to milliseconds. So, if we basically measure the intensity of the scattered light in microsecond, then we will see that the intensity signal is fluctuating with time. But if we can consider a longer time, then we can consider this as the average intensity of light. So, we can call this as a average intensity, scattered intensity of light. Now, we can use both information, the average light scattered intensity and also the fluctuation in the scattered light in a smaller time frame. So, this fluctuation can be used to analyze the intensity to find out the hydrodynamic radius, which is a principle of dynamic light scattering technique, and this average value can be used to determine this molecular weight and second variant coefficient and the size of the molecule, and the technique is called static light scattering. So, in this static light scattering, we are considering the average scattered light, and in case of dynamic light scattering, we will basically consider the fluctuation in the light intensity. Now, this we will go one after one. First thing that we will consider light scattering from one single particle or one single small particle. In that case, the expression for I theta by I 0 is the intensity of the incident beam, and I theta is the intensity at a particular angle, intensity of the scattered light at a particular angle from a single particle, which is given by this expression. So, this expression is for the scattered radiation arising from interaction of a single molecule or single particle with unpolarized incident beam having intensity I 0. Alpha is the polarizability, lambda is the incident light wavelength, r is the distance as shown here, and theta is the scattering angle. Now, alpha is the polarizability of the molecule, which relates to this term dN by dC square. dN by dC is the refractive index increment at basically if we plot refractive index of a solution with concentration, then slope will be the refractive index increment, and which is related to alpha. Hence, the scattered light intensity for a small single particle is proportional to dN by dC square. Now, we will move to from one particle, we will now move to many gaseous particles together. Consider a volume V of a dilute gas having n gas molecule. Now, in this case, total intensity of the scattered radiation per unit volume of dilute gas is given by this expression, where dN dC we have discussed, the refractive index increment, which is the linear rate of increase of refractive index with gas concentration. C, again C is mass per unit volume. Now, this is expression is the Rayleigh equation for ideal elastic scattering of unpolarized incident beam. Now, in this case we are talking about the size of the particle are small, actually less than, the size of the particle is less than approximately lambda by 20, or sometimes we call lambda by 50 depending of different sample, where lambda is the lambda dash, we can say lambda dash is the wavelength of the light in that solution. So, if we have seen this expression. So, we just bring those expression in this slide, and in this case the scattering envelope is given by this, is basically looks like this. So, this scattering angle is 90 degree here, and this is 0 degree, this 90 degree, this is 180 degree. So, if we write this is 270 degree then. So, in this case this is the scattering envelope or the variation of this shown in 2D. You have to imagine in 3 dimension term, where the scattering intensity is plotted against the scattering angle, and the variation of this intensity from a sample is symmetrical in this particular case. When we mention symmetrical, we mean that I theta is same as I 180 minus theta. So, basically we have a symmetrical shape, and these happen for small molecule, and as I said that this is not a fixed number. We can sometimes we can write this as lambda by 50. So, basically that number is not very well defined, but for a small particle, when the gas molecules are small, then we have this type of scattering overlap. Now, if we rearrange this expression and write R, which is a term Rayleigh ratio, then this variation of R with theta will now be like a spherical, which means the value of R will not depends on this R or theta, because the variation is taken care of in this term, and we call this as a symmetric scatterer. So, symmetric scatterer means the scattering happens in this way, where I theta is I 180 minus theta, and the Rayleigh ratio is not dependent on the scattering angle or theta. Now, we now talked about single molecule, then a gaseous mixture or a cluster of gaseous molecule. Now, we will talk about liquids and solution of small molecule. Now, light scattering does not only happen due to the interaction between the molecule and the light, but it also happen due to fluctuation in the concentration of solvent molecules as well as solute molecules. So, there are light scattering due to fluctuation in local concentration of solvent as well as solute molecules, in this case polymer solutes. Now, this fluctuation happens because of change in local temperature, very minuscule local temperature change or pressure change, and as a result scattering happens also due to this fluctuation in the concentration. Now, we can take care of the solvent contribution by simply subtracting the scattering due to solvent from the solution. So, we are writing this as a excess Rayleigh ratio. This is called excess Rayleigh ratio, which basically take care of the removes the scattering due to solvent molecule from the solution. So, we need to take care of the polymer solutes. Because of the local fluctuation in polymer concentration, there will be local osmotic pressure generation, and we can actually use, as suggested by these two scientists, we can use expressions similar to osmotic pressure and use this excess Rayleigh scattering. We can get a expression like this. So, this is where we are taking care of both the fluctuation scattering due to fluctuation of solvent molecule and due to the fluctuation in the concentration of polymer molecule. And if we simplify this expression by writing K as this, these are the constant term for the equipment and the solvent polymer pair. So, we call this as optical constant. So, we can simplify this expression and write this. So, this is now, this expression is for small polymer molecule symmetric scatterer, which basically in this case we have considered the scattering due to fluctuation in solvent molecule and concentration in solvent molecule, as well as concentration fluctuations in the concentration of polymer molecules. So, in next lecture what I will do, I will take care of the asymmetric scattering, which means when the solute size or the polymer size become large enough, so that the scattering Rayleigh ratio is dependent on the theta value now.